Hello everyone, my name is Amirul Azizi. Today, I will bring you throughout my final AI for EO project, which is the land use and land cover classification of Sentinel-3 images using machine learning and AI. So, have you ever thought of how do we distinct the difference between ocean, clouds, backgrounds, and trees and vegetations from up high in the sky up to the level of the satellites? Well, thanks to machine learning, we can now no longer need to rely on human interpretability to interpret this land cover region. By implementing AI machine learning models, we can now classify each regions into their own distinctive clusters. For this project, we will deploy two types of machine learning models, which is the unsupervised machine learning, which is the k-means clustering, and the supervised machine learning, which is the random forest classification. K-means clustering is an unsupervised machine learning algorithm that used to group data points, such as image pixels, into a predefined number of clusters based on their feature similarity. In the context of remote sensing, each pixel is treated as a data point with spectral values that serve as an input features. The algorithm works by randomly initializing cluster centroids and repeating this process until convergence. On the other hand, random forest is a supervised machine learning classification that is widely used for classification of regression and thus in terms of land cover classification of remote sensing techniques. It works by constructing an ensemble of decisions at each split as a tree and a random subset of features is considered. This randomness increases as model diverse and to reduce overfitting. When classifying a new data, such as a pixel in a satellite image, the prediction is made by aggregating the votes from all trees in the forest and typically selecting the majority vote. We'll start the code execution by first mounting our Google Colab to our Google Drive and install important plugins such as Pandas. Next, we will import the important plugins such as Request, Pandas, and our operating systems. For the next step, we will do the data acquisition, and here it is important to remember that I have already executed this process beforehand. Therefore, if you try to execute this code, you need to remember to insert your own credential for Sentinel-3 ESA passwords and usernames, and also select your own area of interest and your own time frame. For the next step, we will do the data processing and feature extraction. Here, we need to define the path to our image as defined as sent3 underscore path here. The next step is to load our RGB composites and our NIR bands. And after that, we'll compute our normalized difference in vegetation index and DVI. By using the formula near infrared minus red color over near infrared plus red color, we can produce a good image of the prior information of our vegetation index of the area of interest before we even do our classification. The subsequent process is to plot our RGB composite. Here, we'll get a good visualization of the grayscale of our picture of interest by stacking the red, green, and blue color on top of each other. Now we move to the core parts of the projects, which is the LULC classification. We first need to make sure our NDVI is a NumPy array and clean the data to remove nonce value. And also we need to reshape our NDVI for the clustering purposes. Now, we'll start by conducting the k-means clustering. We set the cluster to be 4 and the random state to be 42. And now, by using that formula, we'll plot our unsupervised LULC classification of our k-means clustering, and it will give us this image over here. It is important to note that the presence of clouds is a major challenge when working with satellite imagery, particularly for unsupervised classification method, which are very sensitive to spectral outliers. Since k-means clustering only provided us with a mere spectral similarity, the color that is produced is technically meaningless. So, we need to assign a meaningful color indicators to enhance the interpretation ability of our classification method. The way to do it is we assign each cluster to each class, which is vegetation, water, cloud, and bare soils. And after that, we will use a meaningful color for our ground visualization, which is cloud set as gray, vegetation set as green, water body set as blue, and our bare soil set as orange. And now, we get a good representation of our area of interest with classification that has been done by our k-means clustering. The next process is to deploy our supervised machine learning, which is the random forest. Random forest works by training each data and take the majority of trained trees data. After executed the steps in the code, we'll get the images, and we can see there's a good range of discrepancies between our random forest and our k-means clustering. This brings us to our qualitative comparisons, where by putting the visual side by side, we can see for this particular image, our k-means clustering did a much better job in terms of classification of land cover region compared to our random forest classification. Next, we will look at our quantitative comparison. We first plot our confusion matrix. Though we don't have a ground truth data, we can see the similarities between the pixels that has been labeled by our random forest and our k-means clustering. We can see there is quite a huge range of differences, which means the two visuals produced by two different classification methods is quite different in terms of the product, in terms of the end products. And our pixel-wise agreements show that only 37.84% of similarities between our random forest and our k-means clustering. Furthermore, we will look at our class-wise pixel distributions. Here we can see the most similarities of classification from our random forest and k-means is indicated at the urban clusters, and the least similarities is at the water cluster. The exact same workflow is applied on our second image that will also downloaded from our Sentinel-3 account and go through the same processes, and we can analyze on our visual analysis. Again, we can see our unsupervised classification, which is the k-means clustering, did a much better job in terms of classifying the land cover region in comparison to our random forest. This time is a bit different because our random forest and k-means show a bit higher of agreement, up to 46.92%, but still we can see from our qualitative visualization, we can see k-means did a better job in terms of classifying our land cover region.